So this array of numbers is Pascal's triangle. Starting at the top, the first row just has a 1 in it. The second one is 1 and 1. And then 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And I want somebody to tell me what the next row would be. So we have these extra rows that Alex put in here, and he says if you take the two numbers above and add them together, you get the next number in the next row. So here we're going to take 21 and 35 and add them together and get 56. And then we're going to take 35 plus 35, so that's 70. And then 35 plus 21, 56. 21 plus 7, 28. 7 plus 1 is 8, and then 1. You can always get the next row by adding the two numbers, and it always starts with a 1. So this keeps going on infinitely. Pascal's triangle isn't a finite size. You could keep making rows in it forever. The kind of interesting pattern of where these numbers come from, we can see we get them by adding, right? But those numbers are actually these numbers. 0, choose 1. 1, choose 0. 1, choose 1. 2, choose 0. 2, choose 1. 2, choose 2, and so on. If we just put that beside, these numbers match up. So 0, choose 0 is 1. 1, choose 0 is 1. 1, choose 1 is 1. 2, choose 0. 2, choose 1. 2, choose 2. 3, choose 0. 3, choose 1. 3, choose 2. 3, choose 3. That's where the numbers actually come from, but Pascal noticed that they also make this other pattern. So we're just going to look, we've seen these questions before. Determine the number of paths from point A to point B if east and south are the only possible directions. So we did this before. Do you remember how we did it? You have to look at how many paths would you have to walk from A to B, and the answer is 6. So you would do 6 factorial, and then divide by the ones that are repeats. So there are 3 east, so 3 factorial, and 3 south, 3 factorial, which is 20.
What if there's a point where you cannot go through?
Well, we're going to look at those other different possibilities. But this is how we did it before. I want to show you also the Pascal's triangle way to do it. And the reason is this method works if it's like an exact shape where everything's just rectangular and there's no missing paths. But when you get into ones that are more complicated, you can't use this method. If we start at A, and we just look at going to this point here, how many ways could you get from A to that red dot? Only one, right? So I'm going to put a 1 there. How many ways could you get from A to this red dot? There's only one way, right? You have to go straight across to it because you can only go east or south. So that's also a 1. And then to here, also still just 1. And then the same thing if you're going down here, there's only going to be one way to get to here, 1 to here, and 1 to here. But then when you start looking at the points inside, if we look at this point, the number of ways to get from A to that point, well, you could go across and then down, so east and south, or you could go south and east, which means there are 2 ways to get there. And if you think about that pattern of Pascal's triangle of adding the 2 previous numbers, we can do 1 plus 1, and we end up with 2. If you look at this point, well, number of ways to get there would be east, east, south, east, south, east, or south, east, east, which is 3. But again, if we think of that idea of Pascal's triangle of adding the two previous, it's going to be 2 plus 1 is 3. So we don't have to look at actually, mapping out the pathways. We just need to add the two previous numbers. What will go in this spot? 4. Because there, we're adding 3 plus 1, and we get 4. Down here, it's 2 plus 1 is 3. And here it's 3 plus 1, which is 4. What about this spot? That's going to be 6. 3 plus 3, 6. And over here, 10. 6 plus 4. Down here, 6 plus 4. And then to get to B, 10 plus 10 is 20, which is what we got here. Now for this question, I probably would have used the first method. It was a fair bit faster. Although, once you get used to doing these, it's pretty quick to do it either way. But some of them, you can't just use that method if they're not just a rectangle like that. So let's look at the next one. This one we could actually do either way. Why don't you guys do it the Pascal's triangle way, and I'll do it the other way, and we'll see if we get the same answer. Can you try it? So here's my answer using the factorial method. Here's my answer using Pascal's triangle. The tricky part about this one is, what do you do when you get to that second rectangle? So you take the 1s, 2s, 3s, and you get 6 at the end of that first square. But then what do? You need to carry the 6's over. Because if you can get to that intersection in 6 ways, from there there's only one way to get kind of down to the next intersection. But if there were 6 ways to get there, then there have to be 6 ways to get here. So carry the 6's down and then continue those. And you end up with 120. And you can use either of those two methods to get to that answer. The next one, however, that factorial method is not going to work. And it's because you have this like lake or something in the middle that you can't walk through. So it says determine the number of pathways from point A to point B if east and south are the only possible directions. Same thing, but you have these kind of missing pathways in the middle because there's some kind of obstacle there. And so we have to use the Pascal's triangle method to get there. So why don't you try that one? There's the answer for this one, 66. You can see there how it's done. You should be trying the last one, which is this. And I'll put the answer up for this as well. You should have 54 for your answer for this last one. And you can see here on the board how we got there.